Um, yeah, there was a slight inconvenience. I'll start from the beginning again.
Seismic analysis overview. So the basic process of conducting seismic analysis is pretty much the same across all codes. This particular process that I have listed here is taken for specifically for the Eurocode EC8, but it maintains its close similarity with RFT and also with many other codes. So first of all is our basic requirement. So what we want is a no collapse and a minimization of damage. We then go for compliance criteria, that is, we go for resistance verification, capacity, ductility verifications, and an effective stiffness in case of seismic actions. We then decide on a method of seismic action. So whether we want to do the response spectrum analysis, whether we want to go for pushover and time history representation. So one of these, we go for these options. We also check the seismic action decision is also made based on the regularity of the bridges. Then finally, we go for the method of analysis, which further in. So for example, if we are choosing the static seismic method or response spectrum method, we go to further details of that. And at the end, we do a final verification. That is whether in case of the pushover analysis, for example, whether the demand is less than the capacity, or in case of other analyses, whether the various results are within the permissible parameters. So coming first to our basic requirements. So the basic requirements are pretty much the same across both the American as well as the European code. We have a non-collapse requirement, that is the structure should not collapse. Under ULS, it should maintain its structural integrity, and even though at some parts of the bridge considerable damage may occur, but overall the bridge should not collapse. And it should also be able to sustain actions from emergency traffic, inspection, and repair should be easy. The SLS requirements are usually along the lines of damage minimization. That is, only non-load bearing or secondary components of the bridge should sustain any damage, if any damage is indeed required to be sustained. So the compliance criteria is basically divided into three major categories. You can see here resistance verifications, ductility verifications, and displacement control. So resistance verification is basically the regions where plastic hinges are being formed should have adequate flexural strength to resist the design seismic action effects. Ductility verifications, as the name suggests, the structure should have enough global ductility to adequately resist the seismic forces without having too much deformation, too much cracking. The control of displacements. Now, even if a structure may be ductile, but too much displacement is also not a good thing. So so there are two basic levels of displacement control, that is global displacement control and member level displacement control, as you can see in this slide. So global displacement, as it suggests, is globally the entire structure should not deform beyond a set limit, while at the member level, it is usually restricted to rotational constraints. Let's talk a little bit about some earthquake resisting systems. So over the past few decades, seismic analysis has been given a very intensive observation, and a lot of theories have now been developed. So over these years, all the collective knowledge now suggests that in case of bridges, the hinge formation is most ideally suited at the base, at the top and bottom levels of the pier support. So plastic hinges at inspectable locations, particularly of elastic design of columns. And abutment resistance is not usually required if it is not an integral abutment. Similarly, for transverse cases, plastic, it has pretty much the same criteria as for the longitudinal ones. just that in case of multiple supported spans, they should have adequate support lengths, and plastic hinges again should be in inspectable locations. But what is not recommended for the case of bridges, or more specifically for new bridges that are formed, is that plastic hinge should not form within the superstructure. In case of girder bridges, cap beam plastic hinging is not recommended, particularly when it causes the girder to sag, because this directly affects the deck. Furthermore, bearing systems that do not provide expected or unexpected displacements as well. For example, rocker bearings, which are relatively stiff in the transverse directions, so these are not recommended. And battered pile systems that are not designed to fuse geotechnically or structurally by elements with the adequate ductility capacity. So what this means is battered systems that don't have enough ductility should not be used in new bridges. Now, in case of old bridges, which were, let's say, constructed about maybe 5 or 10 years ago, they may not have complied with this criteria. So in these bridges, only retrofitting and maintenance checks can be performed. So let's come over to the types of seismic analysis that are available. So seismic analysis is broadly categorized into two types, linear and nonlinear. Each of them is further subdivided into static and dynamic. So on this slide, you can quite easily see what are the various types of seismic analysis that are available to us. So today in this session, we shall be going into response spectrum and pushover analysis in a bit of detail. And towards the end, I will also be showing you the time history analysis, a few aspects of time history analysis as well. Talking about regularity of bridges. Now, this is something that has come. You can expect that the regularity of bridges. Sorry about that. So you can expect that the regularity of bridges is related to the geometry of the bridge. So in case of regular bridges, the engineer will find it very easy to anticipate what the seismic response is going to be. But in case of irregular bridges, what may happen is that the response of the bridge, the elastic response and the inelastic response of the bridge may be very, very different. So in case of irregular bridges, nonlinear analysis is more recommended. So nonlinear analysis cases include the pushover analysis or nonlinear time history analysis. So EC8 recommends that you calculate regularity by calculating an R value, which is calculated from this equation on the slide. And if R exceeds the value 2, the bridge is classified as an irregular shape. Now, Arstoll RFD prescribes a bit more straightforward and more easier to follow rules. There is not much calculation involved. You simply calculate it based on the parameters that are entered over here. So here you have if the number of spans for 2, so the maximum span length ratio is there, and if any of the bridge parameters is exceeding any of the prescribed parameters over here, the bridge is considered irregular. Furthermore, the Arstoll RFD code also makes allowances for the method to be used for irregular and regular bridges. So here you have, for example, UL is uniform load elastic method, SM is single mode elastic method, MM is the multi-mode elastic method or the eigenvalue method, and TH is time history method. So as a rule of thumb, it can be generally assumed that for irregular bridges, pushover analysis is always recommended, even in conjunction with normal elastic methods. Right. So before going into response spectrum analysis, I'd like to just talk a little bit more about two very prevalent methodologies of design when it comes to seismic analysis. First is force-based design, wherein we assume that the elastic response and the inelastic response is similar for a structure when we are this assumed similarity allows us to calculate the earthquake loading FP in the slide by considering a response modification factor R. One of the basic assumptions of this particular method of design is that we are simply calculating the force. We are assuming that the capacity is assumed. What I mean by capacity is assumed is that we are assuming that these deflections or that the response is not exceeding the capacity of the structure. So this is one of the basic assumptions in force-based design. Displacement-based design, however, also takes into consideration the capacity of the structure. So it still makes the same assumption that the displacement resulted from inelastic response is approximately the same as that from the linear elastic response. However, once the design load is found, what is finally to be checked is that the capacity response is larger than the demand response. So that capacity may be either the deflection, it may be the force. So any one of these things can be termed as the capacity, and the corresponding parameter also becomes on the demand side. So now that we've discussed a little bit about the various methods, let's talk about the first method, that is the response spectrum method. So the response spectrum method is one of the most commonly used methods for seismic analysis. So the response spectrum curve is found basically expressed in terms of reference seismic action with a return reference period of 475 years as per the Eurocode, and it can be different for other codes, or it can be same as this code. And of course, the response spectrum is dependent on a lot of things. For example, it depends on the amount of damping, it depends on the class of the structure, it depends on the ground type. So here on the right hand side of this slide, you see the ground type classification, A, B, C, D, E, then S1 and S2. So this classification is pretty much the same across nearly all the codes. So even in AASHTO code, you will find A, B, C, D, E type ground classifications, and even the descriptions are almost exactly the same. The only difference between them will be in the parameters. For example, the SPT parameters, SPT limits may be different. The velocity of the seismic velocity may be different across the various limits, but overall it is pretty much the same. So here, one additional thing in AASHTO RFD that is different from the Eurocode is that AASHTO RFD makes mention of seismic design category, that is SDC. So AASHTO LRFD has the provision of that the engineer can create his or her own response spectrum based on the SDC category and the SDC value, which can be calculated from SD1. So based on these limits, so SDCA is the area of least seismicity and SDCD is the area of maximum seismicity. So maximum seismic hazard, so it is in the order of increasing seismic hazard levels. Coming on to cracked section properties. Now, when you're doing seismic analysis, it is a given that the bridge sections are assumed to be cracked, and for linear elastic analysis, the bridge sections are assumed to be non-cracked for the various loadings. So in terms of what the EC8 suggests, so Eurocode 8 suggests the effective moment of inertia as about 8% of the uncracked added to the effective cracked moment of inertia, which is calculated based on M-phi analysis, based on the moment curvature analysis. So I'll be showing you this M-phi analysis in GSD when we come to pushover analysis. But for the moment, you can rest assured that our softwares are capable of calculating the M5 curvature and the crack moment of inertia for you. The same provisions under the AASHTO LRFD actually go for a slightly less conservative values. So there it was the exact same thing. So it is almost exactly the same formula, but the Eurocode adds 8% of the uncracked section stiffness to it. An additional provision in AASHTO LRFD specifically for RC box girders is that for RC box girders, you can assume that the values are anywhere between 50% to 75% of the uncracked stiffness. But for pre-stressed box girders, it is recommended that no reduction be applied. So at this point, let me show you some of the capabilities of our software. So this is our software Midas Civil. So for those of you who have already used Midas Civil, you may be knowing a lot about it. But for those of you who do not, this is the general interface of our software. And this is the basic model I will be working on. Let me explain a little bit about this model. It is a very simple steel eye girder composite bridge. Simply it is a continuous two-span bridge. So let me show it to you in the solid view. So here you can see in solid modeling. So it has a deck, a concrete deck placed over it and steel girders beneath. So when you want to apply seismic analysis, response spectrum analysis to this sort of a bridge, you can very easily go for it in Midas Civil, we have the option of adding response spectrum functions. So when you click, so here, let me show you what are the various response spectrum functions that Midas Civil supports. So here you can see we have a list of all the response spectrums that are supported. So AASHTO LRFD, Eurocode 8, UBC, NBC, IBC, the Korean, Chinese, Taiwanese, Indian, and Japanese response spectrums are completely supported within the Civil itself. Furthermore, if there is something that you find is not supported, or if you want to add your own response spectrum, you can simply copy paste the response spectrum values into this particular table over here, which is completely Excel compatible. So your own values can also be added. So we can also consider the excitation angle for the major axis of the structure. Various damping methods can also be considered, which I will be showing you shortly. So we have, when we consider damping, so for the most part, most of the codes talk about one of the two, SRSS and CQC. So both the AASHTO LRFD and the Eurocode talk about these two conditions, SRSS and CQC. So SRSS is more useful when the mode shapes are well separated. So, but in case they are not well separated, the CQC combination is more appropriate. And in fact, the CQC combination is usually recommended for nearly all bridges. And you can also add signage to the results. So if you want to consider the signs when combining these mode shapes, so you can use this option over here to add signs, and you can select which mode shapes you want to consider for the modal combination. So if there are some mode shapes that you feel are not important and you want to exclude them from the analysis, so that can also be done. And the damping itself, so Midas provides three basic kinds of damping. So we have modal, which is global modal damping can be considered, or you can specify different damping ratios for different modes. Mass and stiffness proportional, where you can specify the damping coefficients based on this formula. So you have to enter the values of A0 and A1. And strain energy proportional, wherein you can specify common damping for certain groups of elements. So within the same mode, you can have different damping ratios for different elements. And finally, since response spectrum analysis in our software, in fact, in all major FEM softwares, is conducted using eigenvalue analysis. So we support the three major eigenvalue analysis types, that are Ritz vectors. We have the support for Ritz vectors, which are useful when your mass participation is coming at a very high number of modes. We have subspace iteration, and we have lamp source. So let me go back to the software. So here in this case, I can show you in the worksheet, I have defined my function over here. For example, I've used the ASHTO LRFT design spectrum, and I have defined a particular load case. So here, this is the RSY load case where I have put the excitation angle as 90 degrees. So that is the global Y direction. I've chosen the LRFT code from here, and I can choose my modal combination control as well. So from here, I've chosen nearly everything. And you can choose to apply what kind of damping you would like. So by default, if this is unchecked, the damping is selected directly from the response spectrum that has been chosen. So if you choose to apply a damping ratio, you can choose any of the three that I explained in the presentation. And if in case, when you choose the damping method, so for different damping, you would have different response spectra. So in that case, the software would need to interpolate between the response spectra to accurately know which response spectrum is to be used, which response spectrum value is to be used. So there you can choose whether you want to interpolate linearly or whether you want to interpolate logarithmically. Finally, the eigenvalue analysis control that I can show you here has eigenvectors and Ritz vectors both. So once this is done, this is already analyzed. So I can show you. Let me first show you the mode shapes of the structure. So we go into wireframe mode, and here I can show you in the legend. So you can choose to view the mode shapes over here, and it directly shows you the mass participation. So here you have MPM percentage. So in the X direction, we have 97% mass participation in mode 1 itself. If you want, you can also get a tabular view of it. So here you get the tables for the frequency and the mass participation tables as well. So here you can see that coming close to, let's say, about mode 27. So here in mode 27, you can see we have 90% mass participation across all 3 degrees of freedom. Now, the 90% mass participation requirement is common across both the Eurocode as well as the ASHTO LRFT code. And in fact, it is pretty much common across all major codes. So furthermore, we also have the option of getting the nodal results of response spectrum. So if I want the response spectrum values, so I can get the inertial force values here. I can directly get these values. Or I can, if I want, I can also even find the values of acceleration. So in the selected units, for example, here it is feet per second square. So I'm using the unit of Kip feet. Or I can get the tabular results for this as well. So let's say for 3 modes. So here, as I go down, you can see the nodal inertia force in Kips as well as the nodal acceleration. And finally, if you want to just get the base shear and the basic data, you can just go into forces, beam diagrams, and from here I can choose any of the response spectrum load cases. Let me choose FZ. So from here, sorry, Fy in this case. So from here, I can directly get the base shear. Since this is RSY, I have to choose Fy. So I can easily get the base shear at the column levels. And furthermore, since most codes also specify a 130 rule. What do I mean by 130 rule? What I mean is 100% when we choose, let's say, in X direction. So in Rx, it should be 100% of the Rx plus 30% of the Ry. So this is the 130 rule. So 100% of the response in one direction plus 30% of the response in the orthogonal direction. So we can create load combinations for this, and we can get the desired responses for these combinations also. All right, so that was just a little bit about the response spectrum analysis. And as I explained already, the 130 rule that is there commonly across both codes. And one other thing that, one final thing that I would like to mention is the presence of the foundation. Now, the American code describes this very clearly, that in case of a fixed footing, you would have the bridge deflecting in a certain manner. But in case of when the foundation has flexibility, as would be in the case of a real structure, the deflection is slightly greater than when you assume a fixed footing. So in such a case, in such a scenario, let me open up a file for you wherein I have considered a foundation. So here I have modeled a foundation. So here I have modeled a pile foundation for this particular model. And for the soil structure interaction, I have assumed point spring supports over here. Now, Midas Civil is also very good in that there is an option here. Let me show it to you. For integral bridges, here you have the option of directly defining pile springs. So when you select a set of piles, this will automatically select, you will just have to enter some parameters like the pile diameter, the ground level, the coefficient of subgrade modulus, the initial soil module, and just select the soil type. So once you enter these data, these point spring supports for the soil will automatically be applied, and the user himself doesn't have to do too much effort. Okay, so in this case, the deformations I can assure you. So here, let me say for RSX, the deformations will come to the tune of about 1.4, yeah, 0.14 meters. Whereas in the case of the fixed footing, we had deformations of the order of 0.09 meters. So obviously, we can see that in the case of flexible foundations, the response is slightly greater than that in case of a fixed foundation. So for this purpose, the foundation should also be considered while creating the model. So let's come now to pushover analysis. So response spectrum method is basically a method for finding the demand of our structure. Now, if we are conducting displacement-based design, as we normally do nowadays, or particularly in case of an irregular structure, we need to consider the capacity of the structure as well. So pushover analysis basically compares the demand to the capacity of the structure and helps us find what is known as a performance point, that is the intersection of the demand and capacity curves. So demand is a representation of the earthquake ground motion, and it is represented by an estimation of deformation that the structure is expected to go. Capacity is a representation of the structure's ability to resist this seismic demand. And performance is basically whether the capacity is able to handle the demand or not. So one very basic thing is that the demand and capacity curves are made based on different parameters. The pushover curve is a curve between force and displacement, whereas the spectral acceleration graph, the response spectrum curve, is spectral acceleration versus time. So in order to accurately compare them, these curves are transformed into capacity spectrum and demand spectrum by using certain methods that you can see in this slide. So they are both transformed into acceleration displacement spectrum. And once that acceleration displacement spectrum has been created, they can be further transformed into any other spectrum that is needed, like a force displacement, base shear displacement, or so on. Finally, once these spectrums have been created, they are overlapped on each other and are compared to get the final performance point. So one reason now we should, one question we should ask ourselves, why do we want to go for pushover analysis? Because of course it is not an easy to perform analysis. It requires a bit of understanding. It requires a lot of time as well. So why do we want to do it? Well, the estimation of the sequence of it allows us to basically gauge the plasticity of the structure to a more accurate degree. Furthermore, in case of irregular bridges where the nonlinear response is markedly different from the linear response, it is a very recommended procedure and should be undertaken regardless of whether or not you wish to do it. And finally, it adds a certain level of confidence to our basic model. So pushover load cases can now be made. Basically, when we do pushover, we normally apply either a force or horizontal force in increments, or we apply a horizontal displacement in the form of increments again. So this slide basically shows the load increment that has been defined as per EC8. So load distribution method, you can have constant along the deck, and this is pretty much similar to the uniform load distribution method as described by the ASTO code as well. When it comes to Midas Civil, our program supports pushover curves from FEMA 273, Eurocode 8, multilinear pushover curve, multilinear hinge types, masonry model, and user-defined hinge types are also available. Then displacement and force-based control methods are available. We have facility for applying the pushover analysis to truss, beam, wall, and even springs. We can find both performance point and target displacement, and we can perform checks for acceptable performance like drift limitations and deformations or strength capacity. So I've already explained a little bit about our hinge types. So we have FEMA, bilinear, trilinear type, and Eurocode 8 as well. Furthermore, axial force moment interaction. And aside from this, we can also create the M5 interaction curve from Midas GST. So for example, if you have a very irregular kind of structure and you wish to if you are pretty sure that the predefined types will not suffice for this, so you can use our program Midas GST. Let me open up a model for pushover analysis, and let me show you how you can use Midas GST to create an M5 curve and how you can import it into Midas. So let me open the general section designer here. Now, the general section designer is a tool for conducting nonlinear analysis on sections. And let me just import a particular file. So here you can see the circular column that has been used. Now, we can directly import this circular column into GST from Midas Civil itself. And once it is imported, we can specify what kind of nonlinear material property we want to have. So the basic nonlinear properties that you can apply to it are the curvilinear model, bilinear, Kenton-Park, Mander model, trilinear concrete as well. So in this case, I have used the Mander model. And now when I run the analysis, so it creates for me the PM interaction curve, the moment curvature diagram, and the stress contours as well. So this is the PM interaction curve that you can see over here. Let me come over to the stress contours. So here you can see under the given loading, what kind of contours are being created. And finally, the moment curvature diagram. So this is the moment curvature diagram as per the Mander model. So in order to create the idealized curve, in order to get the crack moment and the M5 properties, we have to create the idealized model. So I apply it. So here you can see an idealized M5 curve has been created, and simultaneously we have this heading under here called cracked moment of inertia, I crack, which is 0.0296 under definition of meters. Now once this has been done, we can export this quite easily into Midas Civil. So here you have to specify the hinge length. Now what is the hinge length? Let me go back to the slide. So the hinge length is a parameter that is defined across both EC8 and R-SO-LIFD. So the hinge length is defined basically because if the hinge length is not specified, it may be that across an element you may only have plastic hinge at the ING end, but not in the middle. So the hinge length definition is also important. And so here we have the LP hinge length definition based on EC8. And quite curiously, the hinge length definition in R-SO-LIFD is very, very similar to that of EC8. In EC8, this parameter was just 0.1, whereas in R-SO, this parameter is 0.8. So the R-SO-LIFD has a slightly lesser hinge length as compared to Eurocode, but the overall logic and the overall terminology used is also quite similar. Coming back to GST, so once this has been done, you can just click OK. You just need to name the give a name to the M5 curve, and once you've gone back, so once it has been imported, let me show you how it is imported into Midas Civil. So this is the pushover hinge definition box, and here let me show you the yield properties. So this is the way that you can see it. So these are the yield properties of the pushover hinge, and you can even get into more details over here. So here this is the this is very similar to the FEMA type that it has defined. So even here you can feel free, if the engineer wishes it, he or she can make certain changes to the values if they feel that it is too over conservative or not conservative enough. For the moment, I have used FEMA curves, and let me show you the various controls for pushover analysis. In Midas Civil, pushover analysis can be performed not only for normal pier sections, but also while you have considered the foundation. So we have this support dialog box for point spring supports, where you have nonlinear support type. So even nonlinear springs can be added. So the multilinear spring type that is created during the soil structure interaction boundary conditions, so those can also be included. You can choose your slip type as bilinear or trilinear, and you can choose where you want to stop the analysis. So if you want to stop the analysis at shear component or axial component yield, you can stop it there. Then we have the pushover load cases. So let me show you the pushover load cases. So here we have, you can choose the increment method as a load control or as a displacement control. So here I've chosen displacement control with node 34. So node 34 is the node at the pier cap beam. So here it is being highlighted now. So I hope you can see it. And furthermore, the load pattern can be created in the following ways. You can have static load cases. So the load will be taken from the static load case directly. You can have it in the form of uniform acceleration as well. So the load is converted to acceleration type and is applied incrementally. And you can have mode shape. Now, this is a rather new addition to the theory of pushover analysis. This is because when earlier we used to do pushover analysis, it was basically we were just pushing it along, we were just incrementally pushing the structure along one direction. That basically meant we were restricting ourselves to one mode and one mode only. Now, if this, in the case of an earthquake, the structure vibrates in a lot of different modes, and therefore it may be that the critical plasticity may not be in the first mode, but rather maybe in the second mode, the third mode, or in any of the other modes. So if you want, you can choose it as mode shape, and you can select which mode you want to perform the analysis for, and you can see the plasticity behavior for that mode. Okay, so once this has been done, we can perform the analysis. I've already explained to you the hinge types, and the hinge has been defined as well. So let me show you the hinge status. So this is, I'm showing you the rotational ductility factor, and let me show you the legend of it, which gives more details. So towards the end, as we can see, the ductility factor exceeds 1, and here we can see the lowermost nodes, or the lowermost points are now critical and have failed. Similarly, we can see the status of yielding. So towards the end, so here we can see it is going into it is going into the plastic range. Similarly for, let's say for mode Y. So you can see the plasticity behavior for the different hinges quite easily. Similarly, we have plastic deformation as well. So you can check what is the plastic deformation at the end of it all, and the actual deformation, what is going to be the actual deformation. Furthermore, you can even get the forces and stresses. So if you want, like, what is the force being experienced at a particular step, so you can get that as well. Now, finally, we come to the pushover curve, the crux of our discussion. So now this is the capacity curve that we have for ourselves. I'm sorry. So we have our capacity curve, and for the demand curve, let me choose, let's say, a demand spectrum, let's say C. So I can choose it from here, and automatically we can see where the spectrum is, where the demand is going to be. So we get demand spectrum for different damping ratios. So we have at 5, 10, 15, and 20. So this is the lowermost one is for 20, 15, 10, and 5. So at the intersection points, we can clearly see where it is where the performance points are. So for this particular instance, for this particular model, the performance point is in the elastic range, that is over here, And here we can see the details of the performance point. Okay, so that was a little bit about pushover analysis. As we can see, a little bit of repetition here in the slides now. So I've already explained the pushover hinge and how you can import hinge properties from Midas GSD, or you can choose between the various pre-available hinge types like FEMA, Eurocode 8 from the available options. And here you have the capacity curve again that I have already shown you. And one final thing is the local deformation verification. So local deformation verification is basically a rotation check. So here, let me show you chord rotation check. So you can check whether the rotation, so here let me go to RY. So you can easily check whether the rotational demand is within the within the capacity limits or not. So here you get a very useful Excel compatible report. So this report, in fact, all tables in Midas are Excel compatible. You can simply copy in Midas and paste in Excel. So here you get the plastic rotation and here you get the plastic capacity. Finally, let's come over to time history analysis. Now, time history analysis, of course, is a very complex and a very wide field of study. Normally, when we talk of time history analysis, we generally refer to two kinds of time history analyses that are boundary nonlinear, wherein the structure is elastic, but the support conditions, or rather the bearings, usually are modeled as nonlinear elements. This kind of system is preferred when it comes to time history analysis, simply because it is much easier and has much quicker, much faster analysis time. The other kind is inelastic time history analysis, where the material nonlinearity of the structure is considered. Now, in this case, because if we consider the entire structure as nonlinear and then do a dynamic analysis with it, it may take a very long time. So to consider efficiency, what is done normally by FEM programs and even by Midas Civil is that you consider only some critical parts as nonlinear, and the rest of the parts are considered linear. So it is basically a partial nonlinear time history analysis in that sense. So this slide gives a very brief and very basic overview of time history analysis. So here you have, like for the linear case, you have the basic equation of dynamics, which is slightly different for the nonlinear case, wherein two additional factors come up. That is the factor for viscous damping and a factor for variable stiffness. So in Midas Civil, you have the option of automatically allowing and applying for LRB isolators. So this is particularly useful for the boundary nonlinear dynamic analysis. So lead rubber bearing isolators or friction pendulum isolators are available. We also have spring and dashpot systems available within Midas Civil. So here in this slide, you can see all the available systems like viscoelastic damper, hook, gap, hysteretic systems, friction pendulum isolator systems are also available. So the damper systems, as I mentioned, are viscoelastic damping systems and hysteretic damping systems that are available for automatic modeling. So you just need to enter the pertinent properties, and they can be easily ready for analysis. Then when you want to model the nonlinearity or the material nonlinearity of the structure, so as I said, we do not consider the entire structure nonlinear, just the critical parts, usually the substructure parts like piers and in some instances the abutments. So in this case, we approximate that nonlinearity by applying nonlinear hinges with the inelastic hinge models for the nonlinear dynamic analysis. So in this case, Midas Civil supports the following hinge models. We have kinematic hardening, we have Takeda slip model, and multilinear model. So you can get quite easily, you can get results like the status of yielding, the ductility factor, and hysteresis curves as well. Also, Midas has within itself a built-in repository of all the major earthquakes that happened since 1940. So you can directly choose an earthquake response from this very large drop-down table, and you can automatically enter it, and you can also manually define a uh, sinusoidal response if you want it. For example, for machine vibrations, if you're doing it for, let's say, a plant structure or a factory, and you want to analyze for machine vibrations or some things like that, so you can do a sinusoidal function for that. And these are the analysis types that we can get. So hysteretic graph I have already shown you. You can get easily text outputs for displacement, velocity, and acceleration. And time history graphs at different nodes can also be found. Also, Midas Civil has support for vibration analysis due to walking loads. So recently, particularly after the Millennium Bridge in UK, the pedestrian dynamic loading has been given a lot of attention, since the Millennium Bridge suffered very drastically from the pedestrian dynamic loadings. So since then, even Midas Civil has caught up with the demand and has included the pedestrian dynamic load. So we have the dynamic load generator, which can generate loadings for both the pedestrian loadings as well as it can generate train loads. So if you want to perform rail structure interaction or dynamic rail structure interaction, so in that case, train loads can be automatically generated. Finally, we have what is called an option for multiple support excitation. Now, in case of very, very long bridges, like let's say the Sutong Bridge or the Cable Stayed bridges that are very, very long, they can be beyond 3 kilometers in span length. The arrival time of the earthquake can be different at different pier locations. For example, in this slide itself, you can see at first pier, the arrival time is 1.56 seconds. At the second pier, it is 3.48 seconds. So this lag in arrival time means there will be a different structural response as compared to when the arrival time was the same for all the nodes. So Midas Civil has this facility to account for this phenomenon as well. So let me show you this particular feature in Midas Civil. Okay, so here is a model. Here is a very simple ladder deck bridge model that I have created. And here we have, in the workstream, you can see some general link properties. So these general links are lead rubber bearing isolators. So you can see from here that they are lead rubber bearing isolators, and the nonlinear properties have been defined like so. So these properties are generally available from the manufacturers. So they usually provide documents detailing the nonlinear and the linear material properties of their isolators. So now that these isolators have been created, I have also applied the general link property. So here, let me show you. Let me zoom in. So here, I hope that you will be able to see this very small general link that is representative of the LRB isolator. And this is an already analyzed model. So here I have created time history load cases, and this is the response, the earthquake loading that is being applied to the structure. So a ground acceleration has been applied. And a time varying, so the dead load, of course, has been converted to a time varying static load, so that in the load case, if you see over here, in the load case, the dead load has actually been considered. The presence of the dead load has been considered for the time history analysis. So the dead load is also playing a part in the response of the structure during the earthquake. Finally, once this is done, let me show you the response of the structure. So here at different points, you can see the response of the structure in different ways, how it is responding. And of course, we also have the facility to animate this particular case. So you can even animate it. So if I go for a basic recording, I will be able to view the animation of the structure. Now, while the animation is being done, let me also show you some of the other functionalities of Midas Civil. So one of the functionalities is we have a condensed spring support with a 6x6 coupled matrix for accounting for mass and damping. This is particularly useful when in case of bridges, like for example, you can see in this slide for skew type bridges, the dynamic response of the structure can be somewhat different, and different nodes may have different spring properties. So here you can manually specify the general spring support type, and you can manually specify the stiffness matrix of your particular spring and apply it. Finally, we also have the facility of performing soil structure interaction with the kinematic, together with the kinematic hinge model. So, for example, this very complex model, here we performed soil structure interaction together with the kinematic hinge modeling to get an accurate representation of the structural response. So here you can see that the recording is done, and it is, so here I can just put it across and get a very smooth video of how the structure is going to behave. Let me also show you some of the, so you can normally get all the required results like forces, stresses, and let me show you the time history graphs. So here, normally you are interested in some specific graphs. So here I've defined some basic graphs, for example, displacement at pier top. So if I create the graph for this, so it will create for me a graph based on the response of the pier top node with time. So as we can see how the response is varying with time. Similarly, you can get a response for other things like shear or forces as well. And if you want to get the results within the LRB bearings, you can get them from the tables. For example, in the general link. So you just go for earthquake. So here you get the absolute maximum effects due to the time history loading within the LRB links. So the overall purpose of time history analysis is not essentially to design the structure, but rather to observe its response in a realistic earthquake setting. So the structural design is more or less completed from the response spectrum and the pushover analysis considerations. The time history considerations generally act as a checking measure for observing whether or not the structure is safe. Finally, let me end my presentation by discussing with you a few project applications of Midas Civil where the dynamic analysis capabilities of the software were used. So first of all, let me show you, it is the La Jablina Bridge in Durango, Mexico. So here, eigenvalue analysis and response spectrum analysis was used together with the construction stage analysis with time-dependent effects and vehicle load optimization as well. The Basara Viaduct in Romania, which is one of the longest bridges in Romania currently, with an overall bridge length of 1.4 kilometers. Here, nonlinear dynamic time history analysis with LRB isolators was used, and also with viscous dampers. The Stonecutters Bridge, which is the third longest cable-stayed bridge in the world right now, with an overall main span length of 1600 meters. So eigenvalue analysis, buckling analysis, time-dependent effects. So basically, a whole bevy of analyses types was used for this particular bridge. Similarly, Sutong Bridge, which is the second longest cable-stayed bridge in crossing the Yangtze River in China. And here also, eigenvalue analysis, thermal buckling, and basically the whole gamut of analysis capabilities offered by Midas was used for this particular bridge. So with that, I'd like to end today's web session. Once again, a very heartfelt thanks from Midas IT for all our attendees who have taken the time to sit through this web session and to hear me. If you have any queries or if you have any questions at this point, I would be more than happy to answer.
That was the end of the presentation that we that was recorded previously. That's all for what we've prepared today. I'm seeing some questions. Please give me a moment. Yes, PDH credit will be published for this specific elite training seminar too. It will be processed within next 2 weeks and then will be sent out to everyone who attended this webinar. If you have any questions regarding this training session or anything, please send us email at midasoft@midasit.com. Well, this is all we have prepared today, and thank you so much for attending our elite training series, and looking forward to see you in 10th one. Thank you.